Hi there. So now instead of doing self-aldol condensations, we are going to look at what's called crossed aldol condensations, where instead of it reacting with itself as the nucleophile and the electrophile, we're going to throw in another one it could react with. But if you can imagine, that could get a little messy or complicated because you could have self-self adduct, other self-self adduct. This one is the electrophile, this one's the nucleophile, or this one's the electrophile and this is the nucleophile. So that's the danger of having the electrophile and nucleophile capabilities in the same molecule. It could do itself kind of attack or attack with a neighbor. So let's write out all those possibilities. This is called a cross-aldol, and this is what happens when we have two different starting carbonyl compounds, so ketone or aldehyde, that have an alpha H on their alpha carbon. So notice these both satisfy that condition. So we have two acidic H's and we have a base to add. So let's write out, let's kind of organize that because there's those four scenarios. So I'll color code it as well. This first one could be the nucleophile, while the second one acts as the electrophile. And then let's do blue and say, well, how about this one is the electrophile instead, and the second one's the nucleophile. And, oops, I'll change colors here. Let's do green. But we also know we could still do self condensations, right? So why not nucleophile and electrophile for this one, and this one just doesn't react in that scenario. And there's the fourth outcome possible where this one is not reacting because this one is both its nucleophile and its electrophile. So the reality is all four outcomes are possible. It just depends on which neighbor it bumps into first. So if it manages to become deprotonated, it's going to act as a nucleophile, and whoever that nucleophile bumps into, that's how we determine the new adduct. So let's write out our addition products. Notice I'm saying the word adduct. That's how you describe the name of the type of product when you do an addition product. Okay. So, and I'll put an S because there's actually going to be several. Now, from the black path, we have to visualize this, right? Because I'm not going to do the whole mechanism in this small box. If this is the nucleophile, that means the base took off the alpha H, never takes off the aldehyde H. That's not an alpha H. This is the carbonyl carbon. There's our alpha H. So it takes off that H. That means there's a minus there. That's our nucleophile. It attacks, opens, and that gets protonated. So in order to draw that, I'm going to draw the nucleophile intact because it did not open up a bond. It made a new bond right here to this carbon that's now going to have an OH instead of a carbonyl. Okay, so if I track my carbons, which is always helpful to do, let's number these 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, 5. Okay, let's do the blue product. It's the exact opposite. This one is going to get deprotonated by the base, so there's going to be a minus there. So that means this basically stays, that structural piece stays intact. So I'm going to just draw the aldehyde in preparation. And there'll be a new bond to the alpha carbon because that's the one that was the nucleophile. What does that attach to? This carbon that it attacked, that got open the pi bond to become an OH, get protonated, attack, open, protonate, and then these this ethyl chain. So let's fill that in. So new bond, OH coming off of there, attack the carbonyl carbon, and then don't forget your ethyl chain. Good idea to count carbons. They're easy to drop or accidentally add because that new bond makes you feel like maybe you've added a carbon when you really have just connected two carbons. So it's especially easy to drop them. So because we used our, oh, I forgot to draw my aldehyde H, right there. Okay, so we have, this was carbon 4 and 5 because we used the aldehyde in that scenario that was smaller. And then it attacked carbon 1, which has 2 and 3 attached. So we have we've accounted for all the carbons. Okay, outcome 3, this is nothing new. This is the self-aldol. So the first one, propionaldehyde, reacts with itself, or propanal, this is also called, self-reacts. So draw intact, Then draw where the new bond will be on the alpha carbon and draw it attached, except the carbonyl changes to an OH. And we can number our carbons there. It's going to be 1, 2, 3, attaches to 1, 2, 3. And then finally, in red, self-aldol with ethanal, 2-carbon aldehyde. So draw our aldehyde intact. That's going to be their nucleophile, new bond, and then it's going to open up to the OH with only a methyl attached. So that means we have 4, 5 bonded to 4, 5 when you track all those carbons. So 4 possible products. I'm missing an N there. 4 possible products. Not even counting for stereochemistry. We're just talking about different unrelated products. They're not even isomers, right? Okay, so here's the problem. This is not desirable usually to get 4 possible products, right? So if we did this in the lab, there's an emoji for our reaction. It would be this unhappy chemist right here. Just a big mess because we want to optimize conditions so that we get 1 product at a time. Otherwise, you're dealing with lots of purification that has to happen before you can actually collect the product you want. No one wants to get 4 products at once. But it can be very useful to do a crossed aldol because we might not want a product that only reacts with itself. We might want something that there are 2 crossed versions where these 1 and 2. So let's label that. I need to move it out of the way a little bit first. Crossed. So we might want either the black or the blue product, right? But there are better ways to go about it that deliver more control from the chemist's point of view. So when would this be useful? Okay, so some ways to avoid having 4 possible products can happen when, suppose, the trouble came from the fact that both of these could act as both a nucleophile and an electrophile. Can we control who gets to be the nucleophile? Because a nucleophile is a reactive step where it requires removal of alpha H. How about if one of these 2 has no alpha H? That means the other one is the only one that could be the nucleophile. So that dramatically lowers the number of products, right? So when one carbonyl has 0 hydrogen atoms on the carbon, when that happens, the carbon with the hydrogen atoms on the alpha carbon will form the enolate, hence i.e. our nucleophile. And the carbonyl with 0 hydrogens on the alpha carbon will be the electrophile. So let's look at an example where this will happen. So if we put in the right ratio of base, so it's one of these to one of those, that means that this one could get deprotonated because it has the alpha H. Notice how this one has no alpha H, no H there, and there's no carbon there to have an alpha H. So this is the only one with an alpha H. So I'm going to draw in its H. So therefore, this is only the electrophile. Okay, so let's draw in our alpha H on that one and attack it. Deprotonate, leave behind, and that's going to form our enolate. Oops, it is in equilibrium, but I didn't mean to draw a resonance-looking arrow. So we have this. Okay, and so now it can go ahead and attack our electrophile. So I'm going to call this phenyl ring pH, just to save a little space. Attack open to a negative charge. And that also had the aldehyde H. So that's the electrophile pieces. New bond, alpha carbon from the aldehyde nucleophile, and the rest of the aldehyde drawn in. And then of course we neutralize. And then we can, I'm going to start drawing in the whole thing. Okay, that's the addition product. Notice that if we stop here, we would call this the addition product. Read your directions carefully, because if it tells you to draw the addition product, that's the addition product. But if you say major product, we have to say, well, will it stop at the addition? Or remember, it could also move on to the alpha, beta unsaturated carbonyl if there's extended conjugation especially, or heat. So notice that because we have a conjugated pi system already as part of the R group, that if we were to go ahead and eliminate here and make our alpha, beta unsaturated carbonyl, that we would have a long continuous chain of extended conjugation. So that is actually favorable. So what does that mechanism look like? Which, let's put our H there. We do basically an E2, even though hydroxide is, once again, we've mentioned this, it's a terrible leaving group. It's just we're basically trading one for another. It's already present. But the driving force is the fact that we make this highly conjugated product as a result. And ta-da! There's our alpha, beta unsaturated carbonyl, our only product. Much better than 4 products. You might say, wait a minute, why don't we still get the self? Why don't we get the self? It's the stoichiometry, right? So if we add a 1-to-1 ratio of this, then we can actually hope that it sits around and deprotonates almost everything. Then once this is fully deprotonated, it's not going to attack itself because it's all in equilibrium, right? But if we have the right stoichiometry, this can be fully deprotonated. Then you can add that in. So you could even kind of do it sequentially in reality to further promote the selectivity for one product over a mixture of products. Another control, so chemists like to make sure that they work smarter instead of harder, and making 4 products is working hard because then you have to do horrible purification. But if you plan smart, you can actually plan for 1 product. And so that was a smart plan. Another smart plan is if you have designed in the molecule you're working with, one of the carbonyl containing compounds has a significantly more acidic hydrogen than the other. This is actually exploited a lot. So you use your Cario sort of foundation to say, if I throw 1 equivalent of base to these 2 starting materials, which one alpha H is going to come off first? That's the idea. So in other words, let's flesh that out. In this case, the more acidic carbonyl forms the enolate, of course, and the other carbonyl gets to be the electrophile. So here's an example where we see this happen. In fact, this is kind of a favorite substrate. Notice our alpha H, or alpha carbon. We'll find our alpha carbons, go look for them. Here's our alpha carbon here, here's our alpha carbon here. Notice the H's we're comparing. And I'm going to draw 2 and draw 1 H off. Which one would you rather take off if you're a base? Well, this one's more reluctant to give up its proton because it only has resonance one way, whereas if this one gives up a proton, we have extra resonance between these 2 oxygens. So this is much more acidic. Therefore, this is the enolate, i.e. nucleophile. All right, so let's draw the mechanism. I think these will get pretty obvious after a while, but it's always good to get more practice. Simple acid-base mechanism here to form our enolate. Okay, now it can attack. And yes, I'm going to draw the aldehyde without the H attached. Sometimes we do that. I personally prefer to add the H, but it's good to see a variety. Attack, open. So our crossed aldol with preference for one of them being the enolate. That's, I'm writing so big that I'm going to have to be kind of careful. Let's zoom out a tiny bit. Okay, so enolate gets drawn intact. new bond to where the alpha carbon is, opened up to O minus, which will eventually be protonated to become an OH, right? And then whatever the R group was on the thing it attacked, which happens to be methyl in this case. Okay, so sorry, I'm going to go outside the box a little because I took up so much space in the beginning. Neutralize. And then decide if we're going to stop at the addition or move forward to conjugate further. Now I think we can kind of see the writing on the walls with this one. If we let it keep reacting to dehydrate, we will get more conjugation than just a simple alpha beta unsaturated carbonyl because we have the extended conjugation. So we're going to go ahead and do that. Okay, so where do we take it off? We always take it off the other alpha H so that we can have that conjugation go with those carbonyls and kick off the leading group. So that's our dehydration step. The H is removed and so is the OH, hence we lose the H2O. So we did the dehydration. So draw out our final product. Once again, enolate looks like it's still intact. Dehydrated and methyl from the other starting material. So that's another way to add control. So that's the crossed aldol. Crossed aldol is best if only one gets to be the enolate, in other words, either because there's no alpha H on the other one, so it would never be the enolate anyway, or the other alpha H is not as acidic as the one you want to be the enolate. So there's a strong preference for one to be the enolate. If that doesn't work out for your synthetic plan, it's good to have some flexibility. We can do a directed aldol, and I mentioned doing stepwise. So we say, how about we add the base to the thing we want to be the enolate and let it sit with stoichiometry. And that works just fine if there's a strong preference for one of those to be the enolate over the other. But if there's not, like take these two, for example. This is actually from the previous problem. We don't want to see, so look at this is ethanal and propanal. So I'm basically taking it from the previous problem, and I'm actually going to show that, not the previous, a couple problems ago. So let me go back for you. Look familiar? Propanal, ethanal, and we got 4 products. I'm going to show you a way, and those are the addition ones. If we went on to eliminate, then we will draw both if we need to. So those are 4 addition products. I'm going to show you that we can actually preferentially form only one. So how do we do that? And which one am I going to form? Let's see, I'm going to let the ethanal be my nucleophile. So that would mean it's going to only form the blue product. Okay, so let's go to, sorry, I got, there we go. Okay, so if I let this be my nucleophile and want this to be my electrophile, I could do 2 steps. Extra strong base, LDA. So that's key, is more than just hydroxide. LDA is much stronger. And that will essentially assure us that the equilibrium is resting on the side of forming the enolate. So what does that look like? LDA is lithium diisopropyl amide. Amide meaning a negatively charged nitrogen anion. Those diisopropyls are attached, and then lithium is the counterion. And just to remind you, I know that's a famous base, but don't want you to forget about it. Okay, I'm going to draw on my alpha H, and step 1 gets us to the enolate. The ethanal is the only one that gets to be the enolate because we haven't even added propanal. Propanal has not seen base. Does not get to be the enolate if it doesn't touch base, right? Does not get deprotonated. It's in a separate jar somewhere. So we let this sit and let the equilibrium kind of, so notice this is an equilibrium, but it favors the forward direction because LDA is such a strong base. So presumably you got this after a certain amount of time, you have this sitting in your flask. Then you go measure out how much of this you need and add that to the flask. Okay, so I'm going to draw just the addition product right now. So if we add I'm going to flip this around. And there's my enolate. So how am I going to draw my addition product without showing every little mechanism step if I want to be a little faster? You draw your enolate intact, draw the new bond to the one that's getting attacked, draw the OH, because it always attacks the carbonyl carbon, so the OH comes up off of that one after the new bond, and then everything else attached, H and ethyl. Okay. Count your carbons if you're in doubt. So I have 1, 2, 3, 4, 5. So 1, 2, that was the one that attacked. 2 attacked 3, which used to be a carbonyl carbon, that's why it has the OH on there. 4 and 5 are part of that ethyl chain. So we can make just one by not mixing them all in the pot too hastily. You can actually just do it in 2 steps instead of having, and that's a huge deal. You would not want to be the chemist who had to purify those 4. That would take days, whereas this would be pretty much standard purification technique just to clean it up a little, and you can move on. So much smarter to do it that way. So the strategy is very important, very key. Okay, let's put it all together and have some fun with it. We've been going forward. How do we do this step? How do we do this step? But what does it look like if we see it? Do we know what we needed to use to add it? So in other words, we're thinking one step back again for retro. Okay, so we are going to look for a point of disconnection. And what I always look for is try to spot your alpha carbon of the enolate. How do you know which one it is? That's the one that attacked a carbonyl. And the carbonyl became a carbon with an alcohol. So I see a carbon with an alcohol. Remember, the alpha carbon's always adjacent to a carbonyl. So here's my carbonyl and it has 2 alpha carbons. The one that was the enolate must have been here because it's bonded to a carbon with an alcohol, right? So because it attacked a carbon that was an alcohol. So I'm going to put my point of disconnection right there. That was my new bond. So it means it used to look like this. And that alcohol used to be a carbonyl, and then we had that R group attached. So that's the aldehyde. So we got a ketone and an aldehyde. So if we wanted to make this, what would that forward synthesis look like? We would make sure that the cyclic compound got to be the enolate. So we'd throw that in here first and say step 1. And this is going to probably be our favorite way to do crossed aldehydes, by the way, because the other methods are pretty limiting. They have structural limitations, whereas this one just makes you rely on the fact that we have a strong base and we're not going to add the other thing till later, so it doesn't get to choose whether it's the enolate or not. LDA, and you'll often see conditions for this like THF and even cold, -78°C, because it is very reactive and it's not necessary to heat it. So to avoid overreaction, we keep it cool. And then step 2, we throw in what we need, that aldehyde. I just happen to flip the structure around there. And then we always have a water cleanup, right? Because we attack open, and then step 3 is the water to protonate. Okay, I want to step it up a notch and show you another fun example of mixing the aldol nucleophile and electrophile in the same compound, only this time one part of the compound is a nucleophile, one's the electrophile, so they have to come around and attack. And this can happen if you could form a ring that's a reasonable ring size, like 5 or 6 membered ring. So this is favorable for that ideal ring size scenario. And so if you see this, if you don't see 2 separate things, instead of doing a self-aldol, double check to make sure you're not going to do an intramolecular aldol. How do we know that? You need to number. So what I'm going to do is I'm going to find my alpha carbons. Here's an alpha carbon, here's an alpha carbon, here's an alpha carbon, here's an alpha carbon. One of those 4 gets to be the enolate. And you're going to always pick the one that gives you the best ring size. So I could say, well, if this is the enolate, I get 1, 2, 3, 4, 5, 6. Hey, that's pretty good. Let's see if the other one is the enolate. 1, 2, 3, 4. Yeah, we don't want a 4-membered ring, so that's not going to happen. And because this is symmetric, numbering the opposite way, you'll get the same effect. So go ahead and check that out for yourself. So the winner I'm going to put is the red guy, the red path. Where I started at 1, that's the one I'm picking for the enolate, because if I get to, notice I stop my numbering at the other carbonyl. That means that if this one attacks this one, I get a 6-membered ring. So let's draw that mechanism. Deprotonate, make your enolate. And attack, intramolecular. Okay, so count your carbons again to be safe. 1, 2, 3, 4, 5, 6. So 1 is here, 2 is here, 3, 4, 5, 6. Now we fill it all in. 2 had its carbonyl kept intact. 1 to 6, that's the new bond. 6 has a methyl on it, and it also opened its carbonyl to an O-. And then, of course, we're going to protonate, and let's go ahead and just add heat because I want to drive home examples of dehydration as well. Get us used to seeing both as possibilities, because in reality, that's actually the more common path. And so we protonate, and I'm not going to draw every little step because I know that we know how to do these acid-base steps now, so I'm not going to, just going to write minus water. And we're going to draw our alpha beta unsaturated carbonyl as the product. Okay, so those are actually oddly fun for some reason. You know, the intramolecular, you get to form the ring and you kind of work through the shapes and everything that's associated with that. Let's see what we have next. Is going to change pace. So this would be a good time to pause. I want you to remind yourself of this outcome when we have a leaving group, because until now, we've been doing ketones and aldehydes only. We've been doing attack open protonate. We're not going to have attack open protonate anymore. And so why don't you give that a try? And what do I mean by that? Just draw the template. Okay, so do an attack open, close kick. Okay. I'm waiting. Did you try it? Okay, let's go on. I have to pretend. Let's see. The leaving group and a nucleophile, we always do AOCK. Leaving group means it leaves, close kick. So let's take a look at that. Okay, attack, open. Close, kick. This is just a reminder. Like I said, there's nothing new until the next box where we combine old with new. So this is, you know, this is the template we had many times. We keep the carbonyl because we do attack open and then it closes back and kicks off. That's what we're going to do. We're going to combine that template with aldol. And it's going to have a new name. It's not called an aldol when it does that, because aldols add attack open protonate and then perhaps become dehydrated. Since we don't protonate and have an alcohol anymore, we close Kick, we never form the alcohol, we keep the carbonyl, and that's called the Claisen reaction. Usually Z is an ester. That's going to be the favorite. Okay, so that's all you really need to know, is that let Z be an ester, and that's a Claisen. So I'm just going to call it OR. And we've learned that we can get esters to transform into other groups. So it's not a surprise that that can actually be kind of a leaving group. It's not a traditional leaving group, but the fact that we can get the ester to form another group, right? That'll actually work out okay. Okay, so the nucleophile is going to do the same thing for the Claisen. We're going to take the alpha H. So just form your enolate like you're used to. Notice it says 2 equivalents, because we're going to do the self version first. Okay. Oops, I need to have minus there. So that alpha H is gone. Now we have our enolate. 2 equivalents means we're going to take another one of these esters and do a self reaction, a self attack, just like we did with aldol. Attack, open. So far, same thing. Okay, so our group's hanging down here. Oops, 2 of them. I think that's a little too squished. I'm going to spread them out a little. There we go. New bond. See, that part was the enolate. I'm going to track that for you right there. This was our enolate. New bond. To what? Carbonyl carbon that opened. That carbonyl carbon also had an OR and 2 R groups. Now here's where the mechanism diverges from the aldol. No protonate. Instead, it's close, kick. Big difference, because look at our product. It's going to have a different functional group. So we have our ester on one side that stayed intact because it was the enolate. And lo and behold, we have the other side where we lost the ester. We lost the OR that makes it an ester. And we kept only the groups that were not leaving groups. So let's pause and look at that for a minute. What do we call that kind of compound? Because we have to recognize that. We have to know when we're doing a so-called Claisen reaction. So the best way to probably describe this is the relationship of the carbonyls to each other. So we have a 1, 2, 3 relationship. So we can call this a 1, 3 dicarbonyl, and that's true. And we can even get more specific, because if we say, well, wait a minute, one of those carbonyls is an ester and one is not, can we take it a step deeper than just calling it a dicarbonyl? Since one's an ester and one's not, another way to phrase this is look at the ester, find the alpha carbon, let the other one be the beta carbon, and we will call this the alpha beta. So from the alpha position, we have a beta. On beta, we have a ketone. So it's a beta keto ester. So beta to the ester, there's a ketone. Hence the term beta keto ester. So I like to have that vocabulary kind of associated with it, because when you see a beta keto ester, you want to think Claisen. Okay. Okay, so we are only going to do this with esters. Okay, so let's see if we can do this a little faster. We'll do our cheater shortcut mechanism that's not a formal mechanism, but allows us, if we're trying to solve a problem quickly, and it's okay to do it kind of a shorthand style. But if it's not a mechanism, so I'm going to do short mechanism. We're going to say, okay, if we need to predict the product, I know that one needs to be the enolate. I'm going to go straight there because that's acid-base. I'm not going to show that every time anymore. And I'm going to take its neighbor because it's only has itself as 2 equivalents. So I'm going to take its neighbor. And so half of it gets reacted with half of the ester present, so it's 2-to-1 ratio. Only half of it gets deprotonated, that's this half. The other half stays unprotonated, that's that half. That's the idea behind the equivalence, right? And then it's going to go attack, open, close, kick. That's the shortcut mechanism. And that means I got to flip this guy around because he on the left attacked his friend on the right. So I'm just going to flip the whole thing to look a little bit more like it's supposed to in the end. So I'm putting the ester OR on the left. Okay, so that's my enolate piece right here. It attacked, made a new bond to carbonyl carbon. Excuse me, that's the alpha carbon of the enolate piece. It needs to stay in my blue bubble. Carbonyl carbon, but the carbonyl kept its carbon. The carbonyl carbon kept its carbonyl this time. Didn't lose it because it didn't protonate. It opened, it closed and kicked. Lost its ester, but what did it have? It had a methyl. So this piece here is here. Beta keto ester. We must have done it right. Now notice our choice of base. It matches, you need to match. It matches the ester. Why? We don't want it to get messier. We want to be able to predict which ester we're going to have. So we don't want that thing called transesterification that we know esters can do. In other words, if I had methanol as my base or methoxide, then we would have a whole nother mess unnecessary of MEO here instead of just ETO. So when you're going to set up a Claisen, look at what the ester is, what OR it is. Take that OR, make that your base, RO minus. Okay? Mixed with the same complementary alcohol that pairs with it so nicely, right? Okay, so just like aldols, Claisens can be, we are going to go through the same sort of formal steps. It can also be crossed, not just self. So this concept is reiterated again. So when would this be helpful? Same conditions. What if we had 0 alpha H's on one of the esters? That way it can't be the enolate. All right, so this is actually copied and pasted from the other section. So same scenario. Enolate is the one with hydrogens, and the one without it becomes the electrophile. So case in point, no alpha H's. So therefore, what's its role? Who's it going to be? What do you think? Would you call that the nucleophile or the electrophile? If it can't be the enolate, it can't be the nucleophile. So it's going to be the electrophile. And this will be the enolate. So I'm going to go ahead and just draw in my enolate and visualize that. Can we draw this a little more quickly now? Okay, my enolate always stays intact. New bond, right? So this is for my enolate. Here's my new bond. Attack, open, close, kick. Attack, open, close, kick. To only have the carbon there. This time we didn't get a keto, we got an aldehyde. That's because ketones and aldehydes could both be there. So we have the 1,3-dicarbonyl product with our cross Claisen. They don't match. One's an ester on one side, and the other one was not from the same ester. Okay, other ways we can have useful Claisens that are crossed are when we have the same scenario. One of the esters, an ester is the one of the reactants, and the other one's not an ester. Why? Who is more acidic? It's the same idea as before. The ketone will preferentially be the enolate. It's more acidic than an ester, right? Remember that? That's because the ester has that electron donating group that makes the anion of the conjugate base less stable for an ester. So it actually If there's a base around, it's going to prefer to selectively deprotonate the ketone. So we have the ketone, it becomes the enolate. So here's our ketone here because it's more acidic. So that means this has to be our electrophile. So let's draw in on our alpha H. Let's go ahead and just beeline for that and visualize kind of the quick mechanism to get us to the product. Attack, open, close, kick, and let's draw the consequence of that. Okay, so you know what? I'm gonna rotate this a bit because I think it's going to be easier to look at like this. So notice what I've done. Put it kind of this way. And now I'm going to let this be the alpha carbon that extends and attacked. So new bond. Keep the carbonyl. Keep the R group. Lose the OR. Starting to get the hang of it? Okay, next one, you guessed it. Intramolecular Claisen. Super fun. That has its own name, actually. Just like aldols, we can do intramolecular. I'm going to give you the name. When it's intramolecular, it's still an intramolecular Claisen, but this scientist claimed the name Dieckmann. So it's a Dieckmann condensation. Dieckmann condensation, if it says do a Dieckmann, that means you're going to be doing an intramolecular Claisen specifically. That means you're going to form a ring if you can form, same rules, something with 5 or 6 atoms. And if it can be formed, you're going to go ahead and do the ring as opposed to a self, you know, where it reacts with a neighbor. So intramolecular always happens before intermolecular, right? It's going to react with its own head and tail if it's long enough, then wait for a neighbor to come by. So how would this look? You got to make sure you can form a good ring size. So here's a double ester, a diester in one molecule, and they both have alpha H's. So here's the alpha carbon with the alpha H's. Here's another alpha carbon with alpha H's. So you're going to take any one of those. It looks symmetric, right? Yeah, it's symmetric. So it won't matter which one you pick. It'll be the same outcome. And we'll number and just verify that we could form a good ring size. This time we're going to make a 5-membered ring. I took an alpha H and I numbered 1 through 5. If you're not sure that that's true, that both would have been okay, let's start here. 1, 2, 3, 4, 5. So either one is okay to pick. We'll get the same product either way. If you had a mismatch, like if one could form 4 and one could form 6, you always pick the more stable ring size. Okay, so I want you to try that. Intramolecular, make the enolate, attack, open, close, kick. Check your answer. And then, if you're feeling good about that, then you will be ready when we move on to the Michael reaction, because we need to build that foundation to go to Michael. So give this a try, then move on and check your answer and get ready for the Michael. Okay.